So now let us design a simple counter using JK flip-flop. So a counter is a synchronous sequential circuit that moves through a predefined sequence of states upon application of clock pulses. So an n-bit binary counter contains n flip-flops and can count binary numbers from 0 to 2 to the n minus 1. So let us have an example. So let us design a 2-bit counter to count in the sequence 0001 1011 and repeat using JK flip-flop. So first let us draw the state diagram for this counter. So starting at 00, so present state, so its next state is 01, then 01 would be the present state, then its next state is 10, then 10 become present state of the next state, which is 11, then at state 11, so it will repeat to 00. So next, let us draw the state table. So this is the state diagram. So for the state table, so we begin with the present state. Let's call it PS. Let's say state 00. So its next state is 01. Then at present state 01. So the next state is 10. Then present state 10. Next state is 11. Then present state 11. So it will repeat. So its next state becomes 00. So let's call it variable x to y. Then the next state is x, y. Okay, so using JK flip-flops. So this is the flip-flop inputs. So we have here JX, KX, then we have JY, KY inputs. So for the JK flip-flop, so we have JK flip-flop. So present state, next state, then input to JK. So the excitation table is 0001 1011. So this is 0x, 1x, x1, then this is x0. So for present state 0, next state 0. So this flip-flop input is 0x. Then for 01, so we have 1x, 01, 1x, 10, x1. So 11 is x0, 01 is 1x, 10, x1, present state 1, next state 0. So 10 is x1. Then we will derive the equation for input jx and jx, kx, jy, and ky. So let's start with jx. This is our variable x, this is y. So we have here 0, 1, x, x, so don't care. So we have jx is equals to, so this is variable y. Then for kx input, so we have x, x, 0, 1, 0, 1, 0, 1, x, y. So we have here kx is equals to y. So therefore jx is equals to kx. Then let us derive for jy input. So we have 1 x, 1 x, this is x, y, 0, 1, 0, 1. So we have jy is equals to 1. Then we have ky. So we have x1, x1, x, this is y, 0, 1, 0, 1. Or we have ky is equals to 1. Therefore, we have jy is equals to ky. So we have two flip-flops. So let us draw the circuit. So this is our jx, kx input. Then for our second flip-flop, so we have here for jy input and ky input. So this is x, and this is your x naught. This is y, then y naught. So since this is a synchronous equation circuit that is connected with a common clock, this is for the clock. So let's say this is for reset input. So let's call it clear. Let's call it clear input. So for jx, we have input y, and kx, we have input y. So therefore, this is jx is equals to kx. So the input is y. So let's call it positive y. Then for jy, ky, so this input 1. So this is 1, or basically this is connected to the VCC power circuit. So now let us derive the module for our circuit. So first let us describe a module for our JK flip-flop. So suppose we have here our JK flip-flop. So let's call it in JK. So the inputs are JK. Then we have here Q and Q naught. So this is connected to the clock input. Then let's call it reset N. So for the description of this flip-flop, let's call it module sequential circuit. Let's say JK, using JK flip-flop. So the inputs are, so we have clock, clear, we have also inputs, output X and Y, then input are clock and the clear, so clock, clear, input, then we have the output X and Y. Then we will use the description of this flip-flop. So let's call it module JK flip-flop. So using the behavior model. Okay. So for that module, so we'll use JK flip-flop behavioral. Then we will connect clock to this clock. So that is that clock. So connect to the clock of our circuit. Then so reset N. So we'll connect it with the clear of our circuit. From what else? So we will connect that J. So connected to the input, which is input Y. Then we have that K. So K is connected to the VCC or input 1. So we'll, sorry. So we have K connected to Y, sorry. So that is next Q, or that Q is connected to this output X. The next flip-flop, so we will describe it as JK flip-flop behavioral. So we connect the clock for JK with the same clock of our circuit. Then that reset N connected to clear. Then we have that J. So this that J is connected to input 1. So that is 1 bit, so input 1. Then also for K, that is connected to 1. Then that Q is connected to Y. then AND module. So next we will implement this using Xilinx. Okay, so this is the description of our circuit. So I have here the module. So using Xilinx, so this is our description for the circuit. So this is the one written in Xilinx. Okay. Then for the JK flip-flop, so we have here module for JK. So this is the excitation we use for the JK flip-flop. So now let us simulate the circuit. So the circuit must act as a counter that counts from 00 to 11, then repeat. Okay, so for the simulation, so we have already the test bench. So then I can run So as you can see, it counts from 00, 01, 10, 11, 00. So it repeats. So you can also see on this console the sequence, the counting sequence. Okay, so it counts from 00, so present state, so next state is 01. So present state 01, so its next state is 10. So present state is 10, so its next state is 11. So present state is 11, so its next state is 00. So now we have accomplished design of a simple counter using JK flip-flop.